Previous attempts at creating electrical power via fusion have utilized magnetic field confinement generated by superconducting magnets in order to overcome the electromagnetic repulsion of two atoms. A new approach, spearheaded by Lawrence Livermore National Laboratories, utilizes ultra-fast, high-energy laser pulses to create a massive amount of heat, forcing the atoms to collide at high speeds. This new approach has already seen success, which has led to the CSU Advanced Beam Laboratories' involvement in the project thanks to funding from the DOE. With this funding, the ABL plans to create a brand new laser facility to expedite the research process. Our design team was tasked with reducing the inefficiencies surrounding the target chambers, shown here, where the laser beam interacts with the gases and housings used to generate fusion power. The mechanical team worked on creating a beam splitting chamber, which holds easily swappable optical mounts that adjust the path of the beam. This allows multiple experiments to be set up at any time, which reduces the downtime between experiments and thus increases the efficiency of the lab. Our team's mechanical engineers went through several revisions to get to the final design of the beam splitter. I'll let Carl explain what they hope to show on Edays.
The following image shows our up-to-date design. By Edays, we hope to fabricate a model to scale in the I2P lab to further demonstrate what the chamber will look like. This project has taught us an immense amount of skills in 3D modeling using SolidWorks and the testing of structural integrity and natural frequencies of a product in ANSYS Workbench.
The electrical design team worked in parallel with the mechanical team, creating a system to automate the functionality of the chambers. Starting from scratch, our first semester involved lots of research to create the functional block diagram you see here, which helped us to choose which parts to use. Since high-energy lasers cause a breakdown in air, the final stage of amplification, as well as any subsequent chambers, must be held at vacuum. The primary goal of the automation system is to allow a user to bring the chambers to vacuum, vent the chambers, and open the gate valves connecting the chambers, all while ensuring no human errors can happen, like opening a gate valve between chambers when there's a pressure differential between them. This can cause damage to optical equipment. After extensive research, we decided to create the automation system using a Siemens PLC, which interfaces with an array of HPT200 pressure sensors and solenoidal actuators. These are all controlled via a human-machine interface created with Python. Uriel was our PLC expert and became very familiar with the Siemens Step 7 software used to program the PLC. Ricky worked on sensor integration and spent lots of time figuring out the RS-485 communication protocol used by the pressure sensors. He and Uriel then worked together to get the PLC to read these sensor values, which ended up being much more complicated than we expected. Ross was tasked with creating the human-machine interface, or HMI, using Python. In addition, he worked with Uriel to read all the collected sensor data from the PLC and send it to the computer running the HMI, so that no signal would be sent to open a gate valve without first checking for a pressure differential. For now, all the results for both the mechanical and electrical teams are in either software or simulation. However, to be successful by Edays, we would like to demonstrate a fully functional two-chamber system, as well as show off some scale models of what the mechanical engineers have designed. Thank you for listening. We hope you come see our project on Edays. And with the remaining 15 seconds, please enjoy this clip that was taken right as our lab caught on fire.
Holy shit.